All right, so hi, I'm Natasha Jakes, and today I'm going to be talking about RL fine-tuning of LLMs, which is a topic I'm super excited about lately, and I think many of us are, because I don't know if you saw the DeepSeek R1 paper, but it generated a lot of interest, a lot of hype, affected the news, it affected the stock market. Basically what happened is DeepSeek is a company that was able to train a very powerful reasoning model by applying reinforcement learning. And they showed that you could actually make a smaller model with less compute work effectively with reinforcement learning, which got people very excited. But after this, there were actually a lot of bad takes about this on Twitter that I found a little frustrating. So, just to highlight a few, people were saying DeepSeek proved that RL can work with LLMs, and it kicked off a new RL LLMs era. And even it seems RL might finally be starting to work for LLMs. But the reason I find this kind of ridiculous is we already were in the RL for LLMs era. Let's flash back to 2022 when ChatGPT came out and it kicked off this original hype storm and all this excitement around AI and LLMs. How was ChatGPT trained? What was different about ChatGPT than previous models? Well, it was the application of RL. So if you remember, what happened with ChatGPT is they used this procedure called reinforcement learning from human feedback, or RLHF. And using this procedure, they were able to show that they could train a model with only 1.5 billion parameters, where the outputs were consistently preferred by people over a model 100 times the size that was trained with only supervised learning. And so even in this paper in 2022, the authors concluded that investing in RL fine-tuning is more cost-effective than continuing to scale infinitely. So we already knew RL was really powerful. We were already in this RL for LLMs era. And let's not forget that RLHF is actually what makes models like ChatGPT chat. That's what trains in the behavior to talk to you in a dialogue rather than just sound like you're sampling from the entire internet. So RLHF and RL fine-tuning is a really powerful procedure. But, no shade to the DeepSeek paper because I actually really loved it. I think that paper reads as kind of a love letter to RL. So they say things like behaviors such as reflection, problem solving, these arise spontaneously from interaction with the reinforcement learning environment. It's a captivating example of how RL can lead to unexpected and sophisticated outcomes. We simply provide it with the right incentives, and it autonomously develops advanced problem-solving capabilities. So this is really cool, and yes, this is how RL works. If you set up the right incentives, it can optimize them and learn pretty interesting behaviors along the way. And the whole vibe of this paper actually strikes me as how I first felt when I first got to know about reinforcement learning, when I attended my first big AI conference. And I saw an example of this humanoid robot that had been trained just with RL, purely with only optimizing some objective, to learn some pretty sophisticated movement behaviors. And I thought, this is really cool. And so that's why today I'd like to talk to you about how we can use RL to get sophisticated behaviors in LLMs. And I'm going to start with kind of a trip down memory lane, talking about some of my own early efforts in this space, and then review kind of the modern RLHF era, some recent work we've been doing in the lab, and then just kind of give you a kick in the pants that RL researchers should really think about getting on this, post-training LLM bandwagon, because I think there's a lot of value to be unlocked there. All right, so time for the trip down memory lane into some of my own early work on RL fine-tuning of LLMs. So, back in 2016, as a Google Brain intern, my job was to try to train better music generation models. And, the reason we needed this is because it was 2016. So even though we could train a model on all of the Google Play music data, the problem was the model was an LSTM. So the way that it sounded when it tried to generate music was like this. Kind of weird, bit of a strange pause there. So, what the idea was for my project was to say, hey, what if we could use RL to train the model to enforce some rules of music theory so we could get those compositions to be a little more structured, adhere to these rules? And so the idea was, let's pre-train on data, learn kind of how music sounds, but then keep training with RL to adhere to these rules of music theory. And people were doing stuff like this at the time. They were pre-training on data, and then they continued training with RL to do things like optimize BLUE score for translation. But there's a problem with this approach, which is basically what happens to Homer here. As the RL agent tries to optimize the reward, it will trivially optimize the reward at the expense of kind of erasing everything it learned about the data distribution. Because there's nothing in the RL incentive that says, hey, you need to retain what you learned from the data. And this is a bad thing when you think about applications where we might want to use RL fine-tuning, like music generation or like language modeling, because your reward function is probably imperfect, or you have limited reward data. So in the case of my music theory rewards, it turns out that to perfectly optimize that function, all you need to do is output infinite C's over and over and over again. And so we need to find some way to make sure that the model retains the information it learned about the distribution of data while optimizing within that to maximize rewards. And so my idea at the time was to say, hey, once you've pre-trained on data, why don't you keep a fixed copy of the model around? And we're going to call that a data prior. And it's going to give us the probability of playing a note given the composition so far, or the probability of saying a word given the language. And that's going to be what we learned on data. Spoiler alert, this has come to be known as like a reference policy or a data, an anchor policy. Then we're going to say, let's use that to constrain our RL updates, so that when we're optimizing for RL, we stay within this distribution that we've learned from the data. And so to put that in math, essentially what this is saying, instead of just optimizing to maximize your reward, you minimize the KL divergence between your RL policy and your pre-trained data prior. And this is pretty simple to add to your, for example, Q-learning function. You minimize the log probability under your policy, which is like doing entropy regularization, and you maximize the probability under the data prior. And so at the time, we showed how this connected to prior work on doing KL control, which at the time just did divergence from like a uniform random policy to increase the entropy of the policy. But our key innovation was integrating this data prior that we'd learned from the data. And how does that actually work when you're generating music? Well, let's look at how well this sounds. So there's our original. So much more catchy, right? We had some press come out at the time that kind of called this like a toothpaste jingle, so not sure how much of a massive scientific achievement the composition itself was, but we did find that this KL control technique was really useful. So for example, we were able to show that it improved applications like drug discovery. So in drug discovery, you might have a data set of known drugs, and you can train on that and try to generate samples that look like drugs, but they might not have properties you want your drugs to have, like the quantitative estimation of drug likeness or the synthetic accessibility. So you can optimize those with RL, but you can use KL control to ensure those molecules still look valid and realistic. So, interestingly, this approach has had some staying power. So state-of-the-art LLMs that use RL fine-tuning still use this KL constraint approach to prevent the fine-tuned model from drifting too far from the pre-trained model. So it was used in OpenAI's series of work leading up to ChatGPT, it's used in DPO, and it's used by Google, and it's also still in the recent DeepSeek paper. So this has had some staying power. But in terms of learning from human feedback, we were actually one of the first to do this, where we take a dialogue model and try to actually train it using human feedback. So we made a GPU server where people could chat live with our models, and we would collect the conversations and not only measure explicit feedback in terms of like upvote, downvotes in the interface, but we also tried to look at measuring implicit cues in the text itself. So if the person says something like, that doesn't make sense, we can detect that that's a negative sentiment and use that to train the model. So in a human evaluation, we found, unsurprisingly, the KL control technique was necessary to get this to work well. But we also found that optimizing for things like the sentiment actually led to higher conversation quality than optimizing for manual upvotes, downvotes. This kind of validated our hypothesis that this implicit feedback can actually be better than explicit feedback for training language models. We also did some early work on training language models with self-play. So we did a follow-up where instead of using human data and offline RL, we actually changed to using online RL, where the model talked to a copy of itself, which essentially served the role of a simulated human. And then we actually calculated those same sentiment-based rewards on that. And we found we were able to get even better performance out of those models. So this self-play approach turned out to be pretty promising. And we showed at the time you can use RL to do things like reduce toxicity. So if you train on a toxicity classifier and use that as a reward and incentive to reduce toxicity, RL methods can effectively do that. You set up the right incentives and it's able to optimize them. So that brings us to the modern RLHF era. So RLHF is now, as we learned, super powerful. It's used in most production models, it's used in DeepSeek, but it's also the predominant approach to improving the safety and alignment of LLMs. And this turns out to be a pretty important problem because LLMs are trained on the entire internet. So there's some bad stuff on the internet. You don't want your model to repeat that. So you need some way to ensure that it doesn't output something that's biased, that's unsafe, tells you how to build a bomb, right? But the problem is there's some issues with this kind of simplistic formula. So what is RLHF? So it's actually still a pretty simple recipe. What you want to do is you collect some human feedback data that says, does the human prefer this response or this one? You then use it to train a reward model to predict what the human would give you, what the human's response would be for a novel sample. And that's actually a key innovation that lets you fine-tune the model with online RL, which tends to be more effective than the early work I was showing, which uses offline RL. And so you can sample infinitely from your LLM to produce a bunch of responses, judge them according to the reward model, and use RL training to propagate those values backwards in time and learn how to maximize reward over long responses. And then, of course, once you're done that, profit, right? But I will highlight that RLHF is still a pretty simple recipe. So it involves using this KL control technique, which is something that we talked about, and it involves learning this reward model. And the way the reward model is trained kind of still dates back to this 2017 paper that pulled it from some 1950s preference modeling literature. So basically the way this works is we assume that humans are better at giving comparative ratings than they are giving absolute judgments. So we show the human two different responses. I'm using RL notation here to say one is state A versus state B. And the human says which they prefer. And what we try to do is we say the probability that the human prefers this state should depend exponentially on the reward of that state versus the reward, the average reward in both states. So it's kind of like a softmax function. It's related to maximum entropy inverse RL, if you learned about that in your class. But the key idea here is this is known as this Bradley-Terry-Luce preference model. So what we try to do is we try to maximize the likelihood of the preference data that we observed by learning this underlying reward function R. The problem, though, is we never actually get the ground truth scale of that reward function R. In fact, there are infinitely many R's that could be consistent with a set of preference data. And this is going to cause us problems later. But one of the key issues with this model is that one of the key issues with this model is that it assumes there's a single underlying reward function that can describe all people's preferences that might be using an LLM. And I think that becomes a real problem when we do scale up to the LLM setting or the ChatGPT setting, because there's actually hundreds of millions of users that do have different preferences. And So when we talk about aligning to human values, what are we really talking about? Who are we aligning to? The way these models are trained is actually aligning to a small set of English-speaking raters that have been trained by OpenAI researchers to have high inter-rater agreement in terms of giving these feedback labels with OpenAI researchers. And the values or the preferences that are decided for this labeling process are, again, decided by the OpenAI researchers. And so the training data is coming from OpenAI customers. This is just not capturing the vast range of real human values that you might have in the world. And so this is a pretty impoverished notion of what it means for a language model to be able to support human values. And this has led to recent calls for more pluralistic approaches to alignment. So this is a nice paper coming out of UW. And they outline many different ways this type of pluralistic alignment could be achieved. But for the purposes of our discussion today, what we want to focus on is this type of distributional pluralistic alignment. So really a technical approach to be able to actually model this diverse distribution of underlying preferences in the data. And if you don't do that, it's kind of bad news. So this recent paper, asks the question of, what will this BTL reward model do if you give it feedback from more diverse groups of people? Can it even accommodate feedback from more diverse groups of people? And no, BTL cannot, RLHF cannot. So what will happen is the resulting model will learn to ignore the preferences of minority groups, even if the majority the population only has a weak preference for an outcome that would severely disadvantage a minority group. So this paper, which I encourage you to read, it's great, highlights this example of, let's say I was using an LLM chatbot to be a college admissions support system for people applying to college. The college mainly serves high socioeconomic status people that don't need financial aid. So for the majority of people, they have a weak preference to not see information about financial aid. But for the minority group that needs that information, it's actually very important that they're able to access it. But if you just train that chatbot with RLHF, it would learn to never serve information about financial aid, so severely disadvantaging the minority users. And the reason that this is happening is because the BTL model doesn't actually let us learn anything about the true magnitude of the underlying utilities which are driving people's binary preferences. And so what I'd like to talk about today is an approach that we came out with in our group to achieve more personalized or pluralistic RLHF. And to motivate this further, we really need to respect these divergent preferences, because in language, when the way you actually use chatbots like ChatGPT is you want ChatGPT to personalize to your preferences around your writing style, the level of expertise that you want to have your explanations given at, how concise you like your explanations versus verbose. But in robotics, it's potentially even more obvious. If I want a robot to help me clean up my kitchen and do the dishes, it needs to know where I like to put my plates. And it can't just average over the average location of all plates in all people's kitchens to be effective at the task. So to even be able to successfully do this task, you need personalization. So what does the BTL model actually do with divergent preferences? So if you look at a situation that we constructed where different users prefer that a robot go to different locations. So this group wants the robot to go to the bottom corner, this one wants it to go to the top. If you train BTL on this data and maximize the likelihood under the BTL model, it's going to result in a function that averages these two modes. So it's going to learn a resulting reward function that the robot is supposed to go to the middle. Well, this is actually wrong for everyone. It's now completely useless. It's not adhering to anyone's preferences. So even to just get good performance out of preference data that contains divergent views, we need to be able to account for them. So this is the focus of this work, personalizing reinforcement learning with variational preference learning by first authors Shriyas and Yanming in collaboration with Hamish and Abhishek. And this was presented as a spotlight at this year's NeurIPS. But the key idea here is, instead of this vanilla RLHF reward model that is incorrect for different groups, ignores minorities, etc., we want to make sure our reward function is both personalized and accurate for different preferences. And the way we achieve that is essentially, given a few preference label ratings from a particular user, we infer a latent user vector Z that captures something about this user that explains their different preferences. And we use that to train a Z conditional reward model to recover the true multimodal preference distribution for each user. And the way we accomplish this is to first redefine this BTL reward function to account for a latent variable Z that describes each user's unique preferences. So it just looks like this, very straightforward. We're now just conditioning on Z. But in order to learn that, to maximize likelihood under this model, it's now become intractable because we would have to marginalize over this unobserved Z. So we introduce a variational posterior, an evidence lower bound, but essentially what this amounts to doing is learning a VAE reward model that infers a latent Z from a few preference queries, and then uses that Z to condition the reward function. And then once we've learned that Z, we can actually just condition our policy model on that, so that we can now, once we've inferred what type of user this is, adhere to their preferences more effectively. So how well does this work? Well, check it out. We've now learned these inferred reward functions that are able to disentangle these two user groups and are much more accurate for each group of users. So it seems to have solved this mode averaging problem in the sense that it's accurately predicting these multimodal reward functions. Seems good, right? Bit of a problem. So if you actually look at the scale of the reward function that inferred for these different users, it's varying wildly across users. So it thinks that going to this corner for these users is worth a reward of 450, but going to this other corner is worth a reward of negative 400. And this is because, again, that BTL loss doesn't give us any information about the true underlying magnitude of the reward function. And this is going to cause problems because, one, you now can't compare utilities across users. So you don't really know if preferences for two different users actually diverge for a given state or if they're just wildly different scales. Number two, it's just really hard to optimize. So when you're training this multi-objective RL function where the robot thinks it can get, 10x the points adhering to one user's preferences over the other, then how is it going to trade off fairly for optimizing their different preferences? So this is not getting this equitable solution that we wanted. So how do we solve this? So we decided to borrow this recent idea from SPO and essentially treat the reward model as a classifier. So this means that it has to actually condition on two inputs and decide which one is better. And the way this works is, instead of estimating these raw reward values, we can just do prediction, which essentially completely solves this scaling issue. So now everyone's reward is normalized to be between 0 and 1. So that's good. We found that this is pretty powerful. So in simulated robotics tasks where different users have different preferences for where to place an object, for example, we found that unlike vanilla RLHF, which is the BTL model, or this DPL paper, only our methods are able to get close to Oracle performance in terms of personalizing to the user needs. We find that we can generalize to unseen users, so we're able to only train on a set of 10 users and evaluate on unseen users at test time and do pretty successfully. The reason that this works is because we first train this we first train our model to learn this embedding space, and then we can sample Z's from the prior distribution, so like a Gaussian, and plug those in to our decoder to get predicted different reward functions and train our policy to optimize to many possible reward functions within that space. And that lets us get this better generalization. We're able to scale up to many users, so we can accurately fit reward functions for 100 different users with different preferences, unlike previous approaches. But then potentially one of the coolest things of this approach is what doing this variational model gets us is that we can actually model uncertainty over the inferred latent vector Z. So we can say, how uncertain are we about this user's Z embedding? And what that lets us do is active learning. So we can find a set of preference queries to ask that will most maximize our information gain of Z across all users. So this is actually an approach proposed in a recent Dorsa paper that we adapt here for the language modeling setting. But this lets us do the following, which is with half the number of preference labels, we can get equal performance to having all of them. So that's pretty powerful. So we can drastically reduce how much we need to ask about the user before we can personalize to them. But okay, that's all very well and fine in robot land. But the real question is, can we get this to work for scaled up large language models? And it did take some tricks. It took a significant amount of engineering. So we found that training LLMs to learn a summarized vector embedding is very hard. And prior work has shown that this can lead to drastic performance reductions. You're kind of losing some of the magic of the transformer, where it can have quadratic computation over the input size if you try to summarize into a single fixed length vector. But we were able to get this to work. And the way we did that is through a few tricks. So one, we had to train the reward model for more than one epoch, which is a little atypical in RLHF. But a particular thing that we found was very important is data augmentation. So given that we would be trying to predict the preference that a user has on a particular sample, we would take the other training data for that user and resample many different preference contexts many times. So shuffling the order, shuffling how many labels we had, and we found that this was really important for learning this robust embedding of the user's preferences and not just memorizing specific data points. And we had to have a pretty specific language model architecture, which looked like this. So we found that we use a pre-trained fixed LLM to encode the different statements that the user had preferences over, got an embedding of those, attached it to a preference label, and use a shared paired encoder to encode all of those. So this would be like your encoding of all the preferences we've seen from the user. This can be variable length, so we had a sequence encoder, which is another attention layer, encode all of that into our beautiful Z embedding vector. We do the reparameterization trick to ensure this looks like it's sampled from a normal distribution. And then we take that Z and append it to some new preferences and then predict which one the user prefers. Turns out this is much more effective at being able to model diverse preferences than any prior approach at the time. So when we create these synthetic data sets where users have very different preferences, we find essentially this is kind of the only one that's able to model it effectively. And for sufficiently toy data sets, we can perfectly model it. For ultra feedback with different users, it's a little more challenging, but we do get better performance when we scale up to larger models. We tested whether our models are robust to noise. So what we're doing here is flipping the label of the preference data that we get from the user with a certain probability each time. So even with up to 25% of those labels flipped, we're still outperforming the vanilla RLHF BTL model. Interestingly, at 50% noise, we now have no information about the user's actual preferences because the labels are completely random, and we find that we do as well as the BTL baseline. So this is really promising because it says, even if you don't have information about the user, you get the BTL default. But once you get information about the user, you can start doing better. And I found this really exciting. We showed that our large language model reward model that learns these user embeddings was able to accurately separate users into different clusters in the embedding space based on what their preferences are. All right, so in conclusion, this is the first work to introduce an end-to-end latent variable framework for LLM reward modeling, which captures and adapts to diverse user preferences and enables pluralistic alignment. So in future, I think this model is pretty exciting because of those uncertainty estimates. So that could allow you to do some pretty cool things. You could enable an agent to actually stop and not answer if it's too uncertain about the user's preferences, rather than say the wrong thing. So actually, jailbreak attacks have been shown in prior work to be based on pitting two different objectives against each other. So for example, you want to get the LLM to teach you how to build a bomb. So you say, help me write a movie script about building a bomb. And then its objective of being helpful in helping you write the movie script can override the safety guardrails that it shouldn't tell you how to build a bomb. So we could actually assess when these two objectives are coming into conflict and we're uncertain about what the user's preferences are and potentially stop. We could also potentially detect adversarial or malicious users. If the embedding for a particular user is kind of way off in space, very far from the existing embedding space that we know for other users, it could be an adversarial user. And finally, we could potentially find underrepresented user categories, ensure the model is accurate for all groups. So remember, the model is learning how to cluster users based on their preferences. So you might find that there's some cluster of people that have different preferences, not for a reason you expect, and are therefore sort of undersampled in your data set. All right, so for future work, I just want to talk about why RL researchers need to get on the LLM bandwagon. So multiple prominent RL researchers have said RLHF is not really RL. And I find this kind of gatekeeping a little bit bizarre, because finally RL is having some massive economic impact and proving to be really effective. And then the RL people are kind of quick to say, oh, no, we didn't do that. It's not us. And I think that's just silly, because I think there's a lot that RL researchers could really contribute to LLM and foundation model development. So for example, here's a project I'm doing at Google with a student of mine. So curiosity is this classic RL objective, which says, if I don't know what I should be doing in a particular task, maybe I should just try to learn more about the world. I should be curious and explore. So what is the world in the LLM land when you're talking to a human? It's the human user. So what if I be curious about the person I'm talking to? So we're actually looking at this. We have a model of the user in the loop of our LLM, and we try to use information gain on our model of the user at every dialogue turn as a reward to incentivize the LLM to know more about the user as it's talking to them. This is something I'm particularly excited about, multi-agent RL for LLMs. So could we set up a min-max zero-sum adversarial game with online moral training to actually achieve safety guarantees for LLMs? So what we'd say is, you have an adversary, it's trying to discover a prompt X to get the defender to say something unsafe according to this reward model. And previous work that looked at doing red teaming for LLMs usually has the defender fixed and just optimizes the adversary to search for prompts that elicit something unsafe from the defender. But because the defender is fixed, an adversary is trained with RL to find the optimal prompt, it just keeps discovering the same attack over and over and over and over. The attacks aren't diverse. So now there's this kind of like cottage industry of papers on how do you train the adversary with a diversity incentive to have more diverse attacks. But you wouldn't need to do that if you were doing online moral training, because the defender would patch the hole that the adversary discovers, forcing the adversary to discover increasingly diverse attacks. So we can actually show theoretically that the Nash equilibrium of this game is one in which for all prompts X that the adversary can pose, the defender is able to maximize the rewards. So that's pretty exciting. So this is all stuff we're focusing on in the Social Reinforcement Learning Lab at UW, and if you'd like to learn more, I really encourage you to check out our website. All right, thanks.